the solution. But indeed, we start from allowing some spatial variability in soil water storage over the catchment. Okay. So this varies, this storage, from 0, of course, I already said, impervious soil, 0 storage, to a max that we call Cmax. So we can say 0 minus equal then Ci minus equal then Cmax. We put an upper bound to the storage. So where do I find Cmax? In the most permeable location of the catchment. Typically you find more permeability in the lowlands, and you find less storage in the mountains. But this is just a rule of thumb. Okay, now we assume that this Ci, which is storage of the catchment, is varying randomly. It's a random variable. So what does it mean that it varies randomly? It means that we are not interested in describing for each location Ci. We don't want deterministically say, here I have the storage, here I have this one, here I have this one. Because this would be impossible, and you know, it would require a lot of information. So we are just happy if we could say, if we could describe this variability by introducing a random variable. Okay. We already noted the difference between deterministic and random. Okay, random means that it's something that we cannot describe deterministically with an analytical relationship. So, what is the description that we can use for a random variable? We can describe random variables through probability distributions. So, probability, frequency, remember. We would be just happy if we could say the frequency with which we have this assigned value of soil water storage. So if I could say that I have a frequency of 1/10, 10% of sites in the catchment where Ci is equal to 0, I would be already happy. If I could say what is the percentage of area of the catchment, which means frequency, which means probability, where I don't have any potential for storage, this would be enough for me. Because I could put a rainfall that is uniformly distributed over the catchment, and I know that in 10% of the area, I have no storage. So all that rainfall in 10% of the area is immediately converted into runoff. So this is something that you have to understand, that a description, a probabilistic description, it's enough for me. Because I don't need to know where runoff is originated. I just need to know how much runoff is originated. And therefore, a probabilistic description, which means a description in terms of frequency, which means a description in terms of percentage of the area, it's enough for me. And let me make again this example, and then I close with it. If I could say that in 10% of the catchment, which is an indication of frequency, which is an indication of probability, in 10% of the catchment area, I have no potential storage, no storage capacity, This would allow me to say that if I have a given rainfall to the catchment, immediately, in 10% of the area, the rainfall is converted into runoff, which is enough for me to describe the river flow. So you see that we start from a spatially distributed concept that we aggregate back to a lumped representation in terms of frequency. I think it is an exciting idea. It was a very great idea to recognize that there is spatial variability, to recognize that we don't have enough information in several applications to describe it, and therefore to elaborate the idea of describing the spatial variability with a random variable and its probability distribution. And this is what is written here. In more detailed analytical language with respect to what I said, but this is precisely what is written here. Let's read it. So, for an assigned value, C star of soil water storage, and I assumed 0 in order to be clearer, but we can take any assigned C star value, a probability distribution is introduced that gives the probability frequency that a randomly selected location J is characterized by Cj less than or equal to C star. This is precisely the example that I made by referring to 0. Okay, let's stop here, and then next Monday we will continue this discussion introduction.